the teaching is gonna be, whether it's gonna be a hybrid or there will be,
Yeah, I'm not sure what's the plan for my university. Basically, the entire year was also remote teaching, so we'll see.
So yeah, we'll see how. Because I think in the interspeech at the moment, I think it's a hybrid one. So with some people there, other people taking part remotely.
Yeah. What is the physical location this year?
I think Brno in Czech Republic.
Nice.
So it's a summer. It's actually pretty good location to go to during the summer.
Great location. It's like this kind of vacation town, right, in Czech Republic.
Yeah. So it could have been great. So, but yeah, I think very few people can actually. I think you need to have a special permission to travel on university business. So I think even if we wanted, you'll have to go through a lot of hoops to actually physically go there. So
yeah.
How far in a PhD you are?
So I finished 3 years. I have 1 more year. Hopefully, if everything goes as planned, I can finish in the next academic year. Yeah.
So you had experience of actually going to a real conference?
What?
So you actually had experience going to a real conference?
Yeah. I feel lucky. I'm not sure like when we will return to this physical format. Hopefully soon, but I think this will continue for like 1 or 2 years. Yeah, it's definitely one of the best perks of the field that we're missing out currently.
Yeah, there may be some PhD students that will graduate without ever going to a real conference. So that's quite a pity.
Hi, Herman. How are you? Oh, disconnected.
And he disappeared. Probably pressed the wrong button to unmute. Oh, Herman is back.
Hi.
Hey, nice to see you.
My sound for some reason didn't work. I think the Zoom client on Linux is sometimes a bit strange. Felix, in what time zone are you? Or where are you at the moment?
I'm in Israel. It's 7 p.m. for me right now.
Okay, hour difference. It's good.
Right, I think we can start. We can start slowly the talk. I'll ask Jean to start the recording. Perfect. Thanks, Jean.
Okay. So, do you see my screen?
Yes. Perfect. So now it's full screen. Great. Thanks a lot. Right. Welcome everyone to the next seminar in our series. Today, Felix is going to be talking about supervised to self-supervised phoneme boundary detection using novel neural architecture. So the floor is yours, Felix.
Okay, thank you, Anton. Thanks for the introduction. Hi, everyone. Like I was introduced, my name is Felix. I'm a PhD student from Bar-Ilan University in Israel. And today I will talk about phoneme segmentation, and basically I'll kind of go through supervised to self-supervised with different neural architectures to solve these problems. And please feel free to ask questions. I would much rather have this like a nice conversation than like a formal lecture. So feel free to ask questions, and I will begin. Okay, so the outline of my talk would be something like this. So I will start with presenting the task of phoneme boundary detection. And then my talk will be comprised of two parts. So the first half of my talk, I will basically tell you about a supervised approach for phoneme boundary detection. So basically, I will give you a bit of background. I will tell you about a model that we propose for this task, how we train it, how can we run inference, and I will share some results. And in the second half of my talk, I will focus on another model that we proposed for this task, this time an unsupervised or self-supervised model. And again, I will give you the background, the model, and the results for this approach as well. Okay, so let's start with the task of phoneme boundary detection. So in this task, our input is some audio signal that has a speech utterance. And our goal is to basically predict the time steps at which there was a transition between two different boundaries. So given the audio file, we need to find the times where there is a phoneme boundary. So if we look at this figure, we can see that we have some audio signal. And below, you can see basically how it breaks down into different phonemes. And you can see the phoneme boundaries as the dotted lines. And this is the task, basically, of our model to find these dotted lines. Okay, so why do we need phoneme boundary detection? Why should we invest time in that? So I'll give you some motivation. And I think one of the most classical uses for such systems is for speech sciences. So often researchers in the fields like linguistics are interested in various aspects of human speech. They analyze it psychologically, physiologically. And in order to do that, they need to take the speech and break it down to different components. It might be to measure durations of vowels, to measure the durations of phonemes, measure other phenomena in speech. And basically doing that manually is very hard. So automatic systems can streamline this kind of research. Another field where you can use phoneme segmentation is, for example, for speech synthesis. So many of the recent text-to-speech systems, basically they take as input a sequence of discrete tokens. So it might be text or it might be phonemes, and they predict some kind of audio representation. It might be the actual raw audio waveform or a spectrogram. But in any case, somewhere in the middle, there is something that basically takes the character and predicts the duration that it should take in the resulting waveform. So how can we get annotation to basically train such duration predictor? We can use a phoneme segmentation tool that would output the phoneme durations for each phoneme. And finally, and most recently, there was a paper published by Facebook Research and Google, where they proposed an unsupervised speech recognition system. And basically, one of the inputs to the model was the phoneme boundaries. And the authors also mentioned that basically they took a naive approach of clustering acoustic features into clusters and getting the segmentation like that. But they also said that basically if they had a perfect segmentation of phonemes, that would improve their results for speech recognition. So this is kind of just to give motivation as to why we need phoneme boundary detection. Okay, so now I will start to describe the supervised setting for phoneme boundary detection. And in the supervised setting, we have two options. So the first option is called forced alignment. And in this option, basically, the model gets two inputs. So the first input of the model is, of course, the audio signal. And the second input of the model is a set of presumed phonemes. So the model gets basically two inputs, the audio signal and a set of phonemes that were produced inside this audio signal. And the goal of the forced alignment model is to find a good alignment between these two inputs. And the supervision for this task is the phoneme boundaries. The second setting for supervised speech segmentation, phoneme segmentation, is called text-independent phoneme segmentation. And under this setting, the input to the model is only the audio signal. So we need to predict the phoneme boundaries without any knowledge about which kind of phonemes are present in this speech utterance. So in fact, we're operating on less information than in the forced alignment setting. So today I will talk briefly about forced alignment, but my talk will mainly focus on text-independent phoneme segmentation. Okay. So let's talk about previous work, related work. So basically, we compare again our proposed model against two baselines. And the first baseline proposed here in 2013 is a model that uses like a two-stage SVM model, basically, to predict the phoneme boundaries. While the second baseline uses the expressive power of neural nets, also to solve the task of phoneme boundary detection. And what these approaches share in common is that they both model the problem of phoneme segmentation as kind of a binary classification problem. So let's break this down, what this actually means. So say that we have this neural network that outputs some representation at each time steps. So basically what this paper suggests is to look at each time step individually and attempt to solve a binary classification task for each time step. So let's say that at time 1, there was no boundary. Then we would like to assign the negative class. And let's say that at time 2, there was a boundary. Then we would want to assign the positive class. So whenever there is a boundary, we assign the positive class, and otherwise we assign the negative class. So this is basically the idea behind two of these papers. And I think that what they lack in terms of modeling is basically they take into account the structure of the input, obviously, because they use like a very sophisticated feature extractor like a bidirectional LSTM. But what they don't capture is the internal structure of the output boundaries. And you know that because they are treating each output boundary individually, right? They are optimizing this loss function individually for each time step without considering previous or subsequent output boundaries. So this is kind of our intuition as to what is lacking in the previous work. And we wanted to see how we can address this problem a bit differently and to somehow incorporate this dependence in structure of the output boundaries. Okay, so I will start to describe our model. And again, please feel free to ask any questions. Okay, so say we are given a set of acoustic features as input, denoted here by X. And in our case, X are the MFCC features of the input audio. And let's denote by Y a set of boundaries. So y is basically a vector that contains boundaries of x. For example, y might be equal to, let's say, 10, 20, 30. And in that case, that means that there is a boundary at the 10th frame, at the 20th frame, and in the 30th frame. So this is x and y. And say we also have a mapping function phi of both x and y, which takes these two inputs and maps them to a fixed size vector in RD. So let us now consider the following prediction rule. Our prediction would be a set of boundaries, basically a segmentation. And how do we predict it? We would like to search over all possible segmentations. This is the big Y notation here. And find the one that maximizes some score function. And this scoring function is given by this W matrix transpose multiplied by phi of xy. So again, phi of xy is some function that takes as input x and y, outputs some fixed size representation in RD. We multiply that by W, and we get some scalar that represents how good of a fit is this set of boundaries and this audio signal. And hopefully, if these boundaries really describe the actual boundaries in the audio, this score will be high, and otherwise it will be low. Okay. So this is like really general, but how can we further break this down? So let's look at this phi function. And now we are assuming that we can decompose this phi function in the following way. So now phi of xy is decomposed into a sum. And it is a sum of some other phi prime function that takes as input x and yi. So again, we started with the function that takes an audio and a set of boundaries as input. And now we decomposed it. This is our assumption, basically, that we can decompose it as a sum of some local phi prime functions that each look at an individual boundary yi. Okay, so basically, if you would try to visualize it, it would look something like this. So say that we have this RNN module, and we input it with this acoustic features x1 through x6. And let's assume that we have boundaries at time 1, 4, and 6. Then what would this phi of xy be? It would be the sum of these local phi prime functions that basically take as input x and the individual y boundaries. So this is how this translates to the actual model. We basically take the output representations of the network in all of the individual boundaries, and we sum them together. Okay.
Felix, can I ask you a very quick question?
Yeah, sure.
So, what is the X bar?
So X bar, okay, sorry for this notation. X bar is just, it's just X. It shouldn't be a bar there.
So that's the corresponding X. So in the first case, it's going to be X1. In the second case, it's going to be X4, and so on and so on.
Yeah.
Right? Is there? Am I understanding it correctly that the vector Y can be variable length vector, or is it always has a fixed length?
It can be a variable length. So you can have segments, or you can have 30 segments. You are correct. It can be a variable length.
Right, and is that the main motivation for the decomposition on the left-hand side at the bottom?
Sure, I think it's one of it's one of the reasons, because obviously if you don't know the amount of segments, theoretically, if there was like a predefined amount of segments, you can solve like a multi-class problem or something like more simpler than this. But because we don't know the amount of segments and it's variable, then this is one of the reasons to decompose it in such a way.
Perfect. Thanks a lot.
Great. So I will just remind you that in the related work slide, I told you that one of the areas where the previous work lacked is that they handled basically the output structure, they didn't handle the structure, they just viewed it as individual boundaries. But now I just presented you with a formulation that does exactly the same, right? I'm just treating each boundary separately at the moment. And perhaps this doesn't really make sense. And why not? So let's talk about an example. So say, for example, that we are looking for the offset boundary of a vowel, right? We want to know when the vowel is going to end. And now let's imagine that someone told us if we had any information about when the vowel started, then perhaps it will give us like an insight regarding when the vowel should end, because maybe we know what is the typical vowel length, right? So when we predict the ending boundary of the vowel, it's helpful to know when the vowel started. And so far, like this idea is not really part of our prediction rule. So how can we incorporate that into our prediction rule? So we can modify this rule. And now notice that we have two terms. So we have the term on the right, on the left, which, if you notice, is exactly the same term that I showed you in the previous slide. It's just the sum over some phi prime u's, which are short for unary potential of individual boundaries, right? So this models the boundaries individually and independently. But now we have also added another term here, which is denoted by phi prime b, which is short for binary potential. And now, whenever we predict some segmentation, basically, we also look at pairs of boundaries, right? So we introduce this idea of dependence between output boundaries. And now, basically, this completes the idea that we model the internal structure of the output as well. Any questions about that? Okay. So let's look at the model on the right. Like I told you before, what we did so far was take these phi primes at each corresponding boundary time, and we had these dotted lines. But now, after we have introduced this idea of binary potentials, our model now looks something like this. So now, in addition to the dotted lines, we have these solid lines, which model the dependence between the output boundaries. And practically speaking, we can implement these phi function using RNN networks. So for the unary potential, which is denoted by phi prime u, we just use the output of the RNN network. So let's say phi prime u x y1 is just h1. For y4, it's just h4, and so on. And to represent the binary potentials, so basically, if you would like to represent the binary potential between y1 and y4, we take all of the RNN outputs from y1 and y4, we take their mean, and this is actually the representation for the binary potential. Okay, so this is how these phi functions are implemented. And how do we train this model? Very simply, we minimize the structured hinge loss function, which basically means that we want to solve kind of a ranking problem. We would like for the score of the true segmentation to be higher than the score of any other segmentation with a margin of at least 1. Right? So we're kind of solving a score or a ranking problem now. So this is how we train the model. And now let's talk about the inference. So remember earlier that I told you that in order to make our prediction, we need to take the argmax. So we're searching for a segmentation over the set of all possible segmentations. So if our input sequence is of length n, then the set of all possible segmentations is exponential in the size of n. And of course, going through the entire search space exhaustively is not really tractable. But luckily, we can make the search efficient by implementing a dynamic programming algorithm. And this will bring our runtime to O of n squared. And an important note here is that this search algorithm basically outputs the optimal segmentation according to this scoring function, which means that it might be a segmentation of 5 segments, but it could also be a segmentation of 50 segments. It will find the segmentation that maximizes this scoring function. If for some reason we have knowledge about the amount of actual segments in the audio, we can use a different search algorithm, which not so intuitively will come at the cost of a longer runtime, but we can incorporate a predefined number of boundaries and find the optimal segmentation as well. Any questions about the model so far? Okay, so let's talk about how we evaluate phoneme segmentation models. Basically what we use is the following metrics. We use precision, recall, F1 score, and basically we look at each time step if we predicted a boundary or not, and we calculate the precision, recall, and F1 score for the entire sequence and the entire data set. And we do that with a tolerance window of 20 milliseconds. And this is because basically phoneme boundary prediction is something that happens at a really low temporal resolution, happens really fast. And even humans don't always necessarily agree on the exact placement of the phoneme boundary. So we usually use a tolerance window of 20 milliseconds, meaning we allow for a 10 millisecond error left and right. So one problem with using these metrics is that the F1 score might actually favor a model that has high recall and low precision. Basically, a model that over-segments, it outputs too many phoneme boundaries. So if we take, for example, a really dumb model that just periodically outputs a boundary, every 20 milliseconds it outputs a boundary regardless of its inputs. Of course, this model will have a high recall because it almost surely captured all of the boundaries, but it will have a very low precision. And the problem with the F1 score is actually that it might get a relatively high score of, let's say, 70 or 75, even if it's a really bad model. So in order to kind of mitigate that, we use an additional metric, which is called the R-value metric. So I don't think there is much point going into all the details about how this is implemented, but I will just give you the motivation as to why we use it. So the idea is to somehow penalize models that over-segment their inputs. So you can't really cheat your way around the F1 score because you will be penalized by the R-value score if you over-segment. And for all of our experiments, we report these metrics: the precision, recall, F1 score, and the R-value. Okay, so let's see some results. So we compare our approach against two of the baselines that I mentioned, the SVM one and the RNN one that basically modeled the problem as a binary classification task. And we evaluate our approach on basically all of the models on two data sets, on Buckeye and on Timit. And we can see that basically our model outperforms all of the baselines and on both data sets. Additionally, we also compared our model to forced alignment models. So, and just as a reminder, in forced alignment setting, these models are actually aware about the set of phonemes that is present in the audio file. So they operate with more information than our model, but still we outperform these these forced alignment models. And next, we ran an ablation study. So, as I said, our model minimizes the structured hinge loss function, and we wanted to experiment with additional loss functions and see what their impact on training would be. So the first loss function that we started with is basically the binary classification loss, like I described in the baseline model. So we call this bin, short for binary. And then we experiment with an additional loss function. And so we know that during training in the text-independent setting, we don't know which phonemes are present in the audio file. But let's, just for the sake of the experiment, assume that during training, we have the actual phonemes that are present in the audio. So in that case, we can use these phonemes as a supervision. And so what we did, we basically added a multi-class loss on each time step, where we tried to also, in addition to optimizing our loss function, we tried to predict the phoneme that is present in the corresponding time step. So we call this phone, short for phoneme classification loss. And so if we look at our model, which is called SecFit, and just minimizes the hinge loss function, we see that it already outperforms these loss functions. But then let's see what happens when we start to stack these loss functions together. And we see that if we add the phoneme classification loss to our hinge loss, then we get an improvement of almost 1 in terms of R value. And if we add all of the loss functions together, then basically we get our best performing model, which improves by more than 1 point in terms of R value over our baseline. And so this is kind of like an ablation study. If you have the set of phonemes as supervision during training, then the takeaway from this is that it might help you even if you don't have it during inference. And finally, we wondered what would happen in a cross-lingual setting. And what we did is we trained the model on English data, specifically on Timid, and we tested it on a Hebrew data set. And just like as a note, Hebrew and English only have a partial overlap in terms of their phonetic set. So you might have some phonemes in Hebrew that aren't necessarily present in English and vice versa. Nevertheless, our experiments on Hebrew, our model performed well. It got an R value of 83. And what is more surprising to see is that the model that was trained with English phoneme supervision still managed to outperform our baseline model. And I think that it might happen because basically, even though the overlap is not complete, I think there is a major overlap between these languages. And this is why we basically see still a boost in performance, even if we use phoneme classification of a different language. And this is below, you can see an example of the segmentation of our model, and you can see that pretty much it predicts the boundaries rather well. It missed some boundaries. So like I told you, the model might output a different amount of boundaries than the true label. But it seems that it captures most of the major boundaries. Okay. So I talked about the supervised setting, but in reality, it's really hard to get this kind of annotations. Like getting phoneme boundary annotations is pretty expensive. You need to have expert annotators that know how to do this job. And this, of course, makes it very hard to do in large scale. So then we thought about how can we basically maybe take an unsupervised approach where we don't need these kind of annotations. So I will give you a brief overview of the related work in the field of unsupervised phoneme segmentation. So in 2016, there was a paper called Blind Phoneme Segmentation. And basically, the author suggested to do a really, I think, cool idea. So they trained a language model network that got as input some acoustic features, some acoustic feature set, and at each time step, it tried to predict the next acoustic features. So it's kind of like a language model for acoustic features. And what the authors saw is that if you look at the prediction error of this language model, then you will see that in areas of high prediction, you will most likely see a phoneme boundary. So this is what you see in this figure. You can see the graph of the prediction error as a function of time, and you can see in the red dotted lines the actual phoneme boundaries. And the idea behind that is that whenever we are still in the context of the same phoneme, it is easy to predict the future. But whenever there is a phoneme transition, predicting the future becomes hard. And this is when our basically prediction error spikes. And so what the authors suggested is to look at this prediction error and basically whenever it peaks to predict a phoneme boundary. In 2017, there was a similar paper, a similar idea, but instead of looking at the prediction error, they suggested to look on the activation of some gate inside the LSTM cell, and they found that it also correlates very well with the phoneme boundaries. So this is in terms of unsupervised phoneme segmentation. In parallel, in the field of self-supervised learning, there were two important papers for self-supervised representation learning for audio. And the first is representation learning with contrastive predictive coding, or CPC for short. And the second is called WAV2VEC. So both of these papers suggested a new way to learn the representation for speech in a self-supervised or unsupervised way. And they really had a major impact on the field of speech. So for example, WAV2VEC, it improved the best character-based system of that time in terms of word error rate by 36%, while only using a few hours of label data. And it also outperformed the state-of-the-art character-based ASR system of that time, which was Deep Speech 2. And it did that with like 2 orders of magnitude less data. So it really had a major impact on the field of speech processing. And so our idea was to basically, how can we incorporate these 2 lines of work? How can we incorporate this idea of tracking some function of time and learning some unsupervised or self-supervised representation? So this is what I will talk about in this half of my talk. And before I will start describing our model, I will give a brief overview of the WAV2VEC model. So as you can see, this model is comprised of 2 stages. So the first stage, we get a raw audio waveform, and we pass it through an encoder network, a convolutional neural network, which encodes it into a latent representation denoted Z. Then we take this latent representation and we feed it to another encoding network, which is a recurrent neural network, which encodes it into a latent representation C. So this model is trained using contrastive learning. And in contrastive learning, basically, the authors define this notion of positive pairs and negative pairs. So what are positive pairs? So according to WAV2VEC, positive pairs are pairs of frames that belong to the same context. What does it mean to belong to the same context? It means that actually they are close to each other, temporally speaking. So it can be up to 12 frames of difference. They're still considered to be a positive pair. What are negative pairs? So they are pairs of frames that are not close to each other. So for example, if you sample random frames from random, actually even random files, then these are defined to be negative pairs. And so the goal of the training process is to basically maximize the similarity of the positive pairs and minimize the similarity of the negative pairs. And how do we measure the similarity? So in WAF2VEC, the similarity is measured by the dot product between two frame representations. And if we optimize this model with this task, then what the authors show that if you use this representation, this resulting C or Z representation, then it's very beneficial for downstream tasks. And you can basically show that if you use this representation for ASR, then you can train a speech recognition model with much less label data, and also beneficial for audio classification tasks. But it is not really suited for phoneme segmentation. And this is what I will describe now. Basically, how can we take this idea and adapt it to the task of phoneme segmentation? So any questions so far? Okay, so let's start with formally describing our model. So given a latent representation Z obtained by an encoder network, let's look at the ith frame. So we are looking at Zi, and we define this set called D, which contains all of the frames from the latent representation Z, which are not adjacent to Zi. So again, we have this frame Zi, and we have a set of all of the frames from Z, which are not the neighbors of Zi. So to train our model, we would like to minimize the following loss function. So what do we have here? If we look at the denominator, we can see that we have some similarity measure between Zi and Zi plus 1. And if we look at the denominator, we can see that we have a similarity measure of Zi and Zj, where Zj comes from the set D, which basically means that Zj is not a neighbor of Zi. Sorry. And what this loss function means is that we would like to maximize the similarity of adjacent frames, and we would like to minimize the similarity of just randomly sampled non-adjacent frames. And how do we measure this similarity? So we measure it using the cosine similarity function. So this is how we train our model. And now that we have a trained model, we can define a score. And we define the score at time I, so the score of Zi, to be minus the similarity between Zi and Zi plus 1. So in other words, the score at time I can be interpreted as the model's confidence that the next frame, Zi, belongs to a different segment than that of the current frame, Zi. Right? So in essence, this score function tells us how likely the next frame would be to belong to a different segment. This means that there is a boundary at time I. So let's describe the architecture and visualize this now. So like I told you, our input is just the raw waveform, and it is we pass it through an encoder network, as you can see in this figure. And the encoder is a 5-layer convolutional neural network, which encodes the raw audio using windows of 30 milliseconds every 10 milliseconds. And it outputs this Z representation that I have just told you about. So one of the differences between our model and the WAF2VEC model is, first of all, the depth. So what we found that we don't actually need the additional recurrent neural network. We are fine with just using one convolutional neural network to extract our latent representation. And another difference is, as I told you, in the WAF2VEC paper, because they focused more on speech recognition, they allowed their positive pairs to be really far apart. It could be up to 12 frames apart. But 12 frames of audio is really too coarse of a context for phoneme segmentation. And so we decided that positive pairs are only pairs of adjacent frames. And so we maximize their similarity. And regarding the negative pairs, so like I told you before, they are randomly sampled. But unlike the Wachtufek paper, we found that it's best to sample them from the same utterance. So they can't come from different waveforms, they need to come from the same utterance. And in terms of the similarity, so we found that it is best to switch the dot product to the cosine similarity. So again, to recap this intuition, if we look at adjacent frames, basically, if they are similar to one another, then this basically shows us how likely they are to belong to the same segment. And if two adjacent frames are very dissimilar, then we assume that they belong to different segments, which means that we have basically detected a phoneme boundary at this place. So let's see how this actually looks like on an example audio. So in subfigure A, we have an input audio waveform that we represent here as a spectrogram. We take this audio and we pass it through our encoder network, the convolutional neural network, and we get a representation Z. And so you can see in this subfigure C here that we have plotted this Z representation as a function of time. And what is interesting is that you can already see kind of a separation between different phonemes. You can visually see the boundaries between different phonemes. It kind of looks like that, like there is a barcode for each phoneme. So we take these pairs of adjacent representations in Z, and we look at the score that we defined. And I remind you, the score basically measures the dissimilarity between pairs of adjacent frames. And this is what we plotted in subfigure C. So you can see here the dissimilarity measure as a function of time. And you can see that it correlates very well with the actual phoneme boundaries, which are can be seen here with the red dotted lines. So basically, what we saw is that whenever this dissimilarity measure peaks, we know that there is a phoneme boundary. And in order to predict the phoneme boundary, we basically run a peak detection algorithm on this graph of dissimilarity measure. Any questions about the model? Okay, so let's talk about results. So again, we evaluated our model on Timit and Buckeye against the baselines that I have previously mentioned. And we can see that our model gets state-of-the-art performance on these data sets. And as kind of a side note, I also appended here the results for supervised models. And you can see that there is still a gap between the unsupervised setting and the supervised setting. So this tells us that there is still more work to be done in the unsupervised setting. Next, we ran some analysis. And because we're working with a self-supervised model, so basically we're not really constrained to just using Timit and Buckeye. So we ran an experiment where we augmented each data set with additional samples from the LibreSpeech corpus. So what you see here is we trained the model on Timit, and we also trained the model on Timit Plus, where Timit Plus means Timit plus some samples from LibreSpeech, and the same goes for Buckeye. So you can see that whenever we added additional information from LibreSpeech, additional samples from LibreSpeech, we can improve the results, but the improvement is really not substantial, it's quite minor. But what is more interesting is what happens when we switch the test set and the training set and we look on the cross data set evaluation. So this time we trained the model in Timit and we evaluated on Buckeye and vice versa. And now we can see that for the case of Timit at least, there is a bigger improvement. So we are improved by 3.5 points in terms of R value by adding additional unlabeled data from LibreSpeech. So what does this tell us, basically? So we have an hypothesis about why this happened. So one possibility is that Timid is a small data set. It's not very diverse. And so adding additional samples from LibreSpeech might improve our model's performance. Another possibility might be because the test set of Buckeye is more similar to LibreSpeech. Might be either one. But I think that the takeaway is that really the benefit of working with a self-supervised model is that you can augment it with a lot of unlabeled data. So this is nice. And for this model as well, we looked at the cross-lingual setting. And this time we evaluated these models on, we trained these models on Timid and Buckeye, and we evaluated them on a Hebrew dataset and on a German dataset. So for the Timid model, we can see a similar trend like I previously described. Basically what we see is that if we train a model on Timid, it performs poorly on Hebrew and German. But whenever we add samples from LibreSpeech, the segmentation performance improves, I think, by a big gap. And for the case of Buckeye, we see an improvement with the exception of the precision on Hebrew, but it's really not that big of an improvement as in the Timid model. Okay. So to summarize, I presented two models today. The first is in the supervised setting. And basically the idea behind this supervised model was to take into account the dependence between output boundaries. And we did that by using a structured prediction framework. The second model is a self-supervised or unsupervised model where we used contrastive learning to basically learn a representation that is very discriminative of phoneme boundaries. And then we use the peak detection algorithm to basically predict these phoneme boundaries. And in terms of future work, so like I said, unlike in speech recognition, it seems that there is still a substantial gap between the supervised and unsupervised settings. So there's definitely some place for work in the unsupervised setting. There's still also gap in the multilingual setting. So perhaps we need to focus more on multilingual training and get more data in the multilingual setting. And another direction that we can take is basically take all of this insight about structure prediction from the supervised setting and apply it in the unsupervised setting. So both of the papers that I described today are available on arXiv, and our code is open source on GitHub. We also shared our pre-trained weights, so you can just go ahead and use these models. And I'm available in this email for any questions, any ideas. So thank you for your time. And that's it.
Perfect. Thanks, Felix, for a very interesting talk. Let's see if we have some questions from the audience.